Welcome everybody to your notes on complex numbers. I have a problem on your note sheet to start. Asks you about evaluating the square root of a -4. Now, I think most of us can probably figure out this part because we know that the square root of 4 is just a positive and a -2. So when we put that negative in there, it's really no different than saying you have the square root of a -1 times 4. Well, we know if we break these up individually, -1 square root is just an I, and the square root of our 4 is a positive and -2. So your final answer for this is a combination of those two, saying your positive and -2i. Now, the next question says, what does, or why does it equal this? So I want you to write a little explanation in your own words as to why the square root of a -4 is a positive -2i. Now, as you wrote your video or wrote your sentence, hopefully it was something along the lines of the square root of 4 is a regular positive and -2, and the square root of a -1 is what the definition of what I actually is. So we're going to use that background information to kind of get into something called a complex number. So there exists another system of numbers, the complex numbers, to cover situations that have this good old imaginary unit or our I. So our I is the foundation for all complex numbers. A complex number, which we'll get to in a little bit, has an imaginary part and a real part. But before we get too deep into that, notice here how I have i's to the first, second, third, fourth, all the way up to I to the 8th power. So based on the definition, we technically know what I is equal to. We know that I is equal to a -1, the square root of that -1. And if we ever get this, we know we can simplify this to just a regular I. Well, what happens if you square I? So take the number, the square root of a -1, and you square that. Well, this is giving you just a -1. How do we get that? Because you have the square root of a -1. You square it. We know that these two pieces, the square and the square root, cancel, left with just your regular -1. And there's a little bit of a pattern that will end up developing, because if we have an I to the 3rd power, well, the pattern went from an I to the 1st, that was just a regular I. Your I squared is a -1. That means an I to the 3rd power is a -I. And if we continue with this, and now if we would essentially square a -I, we would come up with a regular old 1. The basis of this is actually something called the unit circle, which you're going to study a lot more when you get into honors pre-calc and a little bit in honors geometry as well. But basically, the way it works is you may say, well, why is this pattern always happening? Why is this pattern always the group of 4? Well, it's all based on your coordinate plane. So if you're starting on your x-axis and you're going to the very first part, this y-axis is just your y value. It's a regular old I. So this is an I to the 1st power, which is the square root of our -1. If we go into the second rotation about this, you might think, well, what numbers lie on this part of the y-axis? Well, that's where we come up with our -1. That's where I squared actually is. So this part is equal to an I squared. We continue all around this until we get to our, in this case, 3rd rotation. It's the bottom part of our y-axis. The bottom part of our y-axis are negative numbers. This is where we get the -I from. This is your I to the 3rd power. And last but not least, as you finish, well, what part of the x-axis are you dealing with here? All of the positive numbers. So this is where you get just the regular old 1 value, which is equal to your I to the 4th. And now, as you keep going around, if you go through another rotation, your I to the 5th power is going to be no different and saying you have an I to the fourth power times an I to the first. Or you go one full rotation around your coordinate plane, you're back to the beginning, and you go one more past that, which is just a regular I. So we know that anytime we're multiplying two exponents together, we actually add them. So we have a 4 times 1 equals our, 4 plus 1 is equal to our 5. We know in this case that an I to the fourth power is a 1, and we know that an I to the first power is just a regular I, so we just found out that an I to the fifth power is also a regular I. We can continue with that for our I to the sixth power. If we break this up, we could say we have an I to the fourth times an I squared. Well, if we actually simplify those, we know an I to the fourth power is 1. We know an I squared is a negative 1, which means this is actually equal to a regular negative 1. So an I to the sixth power is the same thing as a negative 1. And we can continue to do this, and we can use any combination that will equal an I to the seventh. So we could pick an I to the second times another I to the second times an I to the third. As long as those exponents all add up to be 7, you're fine. It doesn't matter how you choose to simplify them. But as we do look at this part, we know an I squared is a negative 1. We have another negative 1. And then our I to the third power is a negative I. When we multiply all of these together, we get our negative I, which is the same thing as your I to the third. And last but not least, this I to the eighth power, this is where, if you're using your pattern, it's hopefully going to really help out, because really it's no different than saying you have an I to the fourth power times an I to the fourth power. 4 plus 4 equals your 8. You end up with a 1 times a 1, or this whole thing is just equal to a 1. You might be thinking, well, how is this going to help us when we get into this bigger pattern of numbers? Well, this I to the eighth power, what it really tells us is that any multiple of 4 will have a final answer. I mean, you're probably wanting to say it already in your head, but it's going to be of just a regular 1. That piece of information is really going to help us out as we get to this now next part, our I to the 13th. Because we most certainly could do I to the fourth times an I to the fourth times an I to the fourth times an I to the first, which means we have 4 plus 4 is 8, plus another 4 is 12, plus another 1 gets you to 13. But that's a whole lot of work. If we recognize that multiple of 4, we could easily say I have an I to the 12 times an I to the first. We know that these two pieces of information now are going to be an I to the 12th is just going to be a 1, and then our I to the first is just a regular I for our final answer of just a regular I. We can continue to use that same property and think what multiple of 4 is really close to 25. That is our I to the 24th times I to the first. Those two numbers will still add up to be equal to 25. So it's really nice because now we get our 1 times I, and this is again equal to just a regular I. You might be thinking, well, do they always equal I? Well, no. With number 4, you have an I to the 98th power. Now again, in your head thinking what multiple of 4 is close to, but still underneath 98? Well, if you're using your calculator, which hopefully you have out on your desk, using it as we speak, you have an I to the 96th times an I squared. And now your I to the 96, since it's a multiple of 4, will be equal to 1. Your I squared in this case is equal to a negative 1. You multiply those two pieces together, and you get a negative 1 as your answer. So you are going to be given random exponents that have I and trying to use your pattern to simplify them into lowest terms. Now, each one of these things ultimately will make a complex number. So notice here how I have an A plus BI. A, in this case, is always going to be the real number, the part that does not have any i's with it. The B is known as the imaginary part, and these two pieces put together are called a complex number. The key here is that A and B are actually real numbers. So an example of what this looks like, we could have a 3 plus 2i. This is a complex number with the real part being the 3, the imaginary part being the 2i. Now, if we're getting back to our nice and wonderful coordinate plane, both of these numbers really stand for the x and the y. The real part is the x, and the imaginary part is the y. Notice how both of them are positive. So you're thinking in here, in your coordinate plane, where do you have a positive x and a positive y value? The only spot here where they're both positive is in quadrant 1. The example that I gave, that complex number is actually going to be in quadrant 1 of the complex coordinate plane. Ooh, mind blown right there, I know. So we're going to do a couple more examples and hopefully help out with that piece. So if we're actually trying to combine like terms by simplifying with adding and subtracting, we're just looking for whatever like terms we have. So in this case, we have a 2 plus 6i that's being added with a 4 minus 2i. We're going to add together the real parts first, the 2 plus the 4. So we end up with a 6. Now we need to do the exact same thing with our imaginary numbers. 6i is no different than saying 6x in this case, and negative 2i is no different than saying negative 2x. So you have 6 minus 2, that will get you a positive 4i. So our final answer in this case is a 6 plus 4i. Now as you're looking at that, you're probably thinking, okay, what quadrant is that in? So we have a positive x and a positive y, so this lies in quadrant 1. So our final answer is a 6 plus 4i, that's actually in quadrant 1. If we continue now to do that same process with a subtraction piece, be careful, and just reminder here that hopefully this is going to finally stick in some of your heads, that we have to actually distribute this negative sign to both of those terms. But now the process is the exact same. Start with the real pieces first. 3 plus your 4 is going to be equal to your 7. We always write our real number first. Our imaginary numbers now get put together with our negative 5i and our minus 2i, which allows us to have a negative 7i. So in this case, you now have a positive x and a negative y. So if you're looking at the coordinate plane, where is a positive x and a negative y? That is going to be in quadrant 4. So our final answer in this spot would be a 7 minus 7i. That lies in quadrant 4. So combining like terms is the first piece of our imaginary numbers, and multiplying and complex numbers is the next part here. The good news about the multiplying our complex numbers is that we have the exact same rules as our exponents. So in this very first example, you'll probably notice that this is the distributive property. So all we have to do algebraically is the same thing as if there was just a regular old x. We end up with a 30 minus our 15i. We make sure this number is in standard form for our complex numbers, the real numbers first, then the imaginary number. We're looking for a positive x and a negative y. We again lie in quadrant 4. So we have our final answer in that respect. If we keep going now and say, okay, now there's an I on the outside, but our still distributive property applies. We wind up now with a negative 4i times 1, which is just a negative 4i. And in this case, we have a negative times a negative, which is a positive. And then a 4i times a 6i is going to give us a 24. But in this case, I squared. Now you notice this is the first example that we've had that has something other than an I squared. And you might be thinking, well, how do we write this in the standard form? Well, I'll give you our rules. You now know what I squared is equal to. If you look back at the beginning of your notes, you know that an I squared is the exact same thing as a negative 1. So what we actually wind up with in this case when we insert that -1 in place of it is a -4i plus 24 times a -1, which means we actually have a -24. If I write this in standard form, I have a -24 minus 4i. And now we have a -x value and a -y value, which means quadrant 3 is where our answer will lie in this case. So the distributive property questions are the exact same, and you might notice what we have coming next. We have a foiling question next. So yes, we still foil in the imaginary and the complex number world as well. So the rules still apply. Everything is the same. So as we're going through, FOIL all this out. 3 times 9 gets you your 27. 3 times a 7i gets you a 21i. Your -i times 9 gives you a -9i. And last but not least, a -i times a +7i gets you a -7i squared. Our goal is to simplify by combining any like terms that we have. And in this case, we have a couple that both have i's in them. So we have a 27. That's just going to stay in front right now. And when we combine these i's, we are going to end up with a +12i. And you'll notice here that we have another I squared in this problem. So if we get rid of that and multiply that by a -1, we are actually going to end up with a +7 at the very end of that. By combining our like terms again now, different like terms, just our actual whole numbers, we have a 34 plus our 12i. We have two positive values in this case, so our final answer would be in quadrant 1. Now, the only way I can possibly make one of these problems a little bit more difficult is just by giving it to you in a different notation. The squared on the outside, hopefully, we remember from our early Honors Algebra 2 days that it just means you have two of the exact same thing. So what I want you to do is I want you to pause this video at this time, try this on your own, and when you resume the video, I will have the right answer up here for you. Hopefully you have now tried this. I will give you the final answer of a 21 minus 20i that lies in quadrant 4. So double check your work, double check your math. If you try to find your mistake, great, ask a neighbor. Or if you got it right, let's keep going on to the very last part that we have. So hopefully if you wanted, you could stop the video, you could try your homework for today's assignment with adding, subtracting, and multiplying. Now this video, the rest of it, is going to look at dividing complex numbers. So when you are dividing complex numbers, your goal is to multiply the numerator and the denominator by this complex conjugate. This is hopefully a word that looks a little bit familiar because this conjugate is the opposite of whatever your denominator actually is. So if we're looking at this very first example with 2 over 7 minus an I, in order to actually divide these two pieces out, we actually have to use some of our multiplication skills. We multiply by the conjugate, which is the positive version of the denominator in this case. Instead of 7 minus I, we are multiplying both by a 7 plus I. Now we actually do have to multiply both of these pieces now. With our numerator, we are going to end up with a 2 times 7, which is a 14. 2 times a positive I gets you a positive 2i. And the nice part, if we remember any of our rules about foiling, when we multiply the 7 and the 7 together, we get our 49. But the reason that we pick the opposite in terms of the signs is that our i's will all cancel. All we have to do is the F part and the L part. The O and the I part are the parts that cancel each other out. So we have our first and we have our last, which end up being a -I squared in this case. As you're looking at this, hopefully you realize that, well, we can simplify a few things in that denominator because we have a 14 plus a 2i, and in that denominator, this I squared will turn into a 49 minus then that I squared of a negative 1. Two negatives right next to one another create a positive. So in this case, we end up with a 14 plus 2I all over 50. And we're so close to our final answer because we can still simplify this by dividing everything in our numerator and denominator by 2. So we end up with a 7 plus I over 25. Now, technically that is one way to write our answer, but we are still going to write our answer in standard form, which means we have to break this fraction up into 2. So we have just the real part added with the imaginary part. That 25 goes to both of your parts in your numerator, and you end up with a 7 over 25 plus an I over 25. You now have the exact same thing that's going to be happening, except it's just a little bit larger scale here. So with the last example, we are going to multiply both pieces by a 9 plus 3I. 9 plus 3I. I'm actually going to start with my denominator in this case, because my denominator, again, will cancel some stuff out. I end up with an 81, and I have a negative number that I'm going to have here. 3I times 3I gets me a 9I squared. And in my numerator, yep, sorry, ladies and gentlemen, you have to FOIL for this numerator. 9 times 7 gets you your 63. 7 times 3I gets you a 21I. You now have a 4I times 9, which gives you a 36I. And last but not least, 4I times 3I gets you a 12I squared. Now our goal here is, again, to simplify this into its lowest terms by combining our like terms. Our middle that we have here is going to still have a 63 added with now our 57I. And again, this I squared is actually a negative 1. We multiply that with our 12, so we actually have a minus 12 at the very end. In my denominator, I have another I squared, so in this case, it's like multiplying by another negative 1. And as I continue to go through, I have a positive 9, which yields a 90 in our denominator. So we have some things that we can simplify in our numerator now. 63 minus that 12 is going to give us a 51 plus 57I all over 90. Your goal is to see, is there any number that goes into each one of these terms? And we can take a 3 out of each one of these terms. So I have a 17 plus a 19I all over 30. If I write this as my final answer, I have a 17 over 30 plus my 19I over 30. Now is your time to practice. Good luck, ladies and gentlemen.